Hi, this is my lab report for Lab 5, Faraday's Law. In this lab, I'm going to explore Faraday's Law on a magnetic dipole and compare the real-life experiment with the computational model in Glow script. And the total time for a magnet to fall through the aluminum foil that I recorded in real life is 1.35 seconds, and the computed value is about 2.759 seconds. And the next slide shows the physical principles that I use in this lab. I use Biot-Savart law to calculate the force exerted on each current carrying ring by the falling magnet, and then use the Faraday's law to calculate the current induced in each ring by the falling magnet. And according to Newton's third law, the force on the ring equals to the force on the bar magnet, so we can use the magnetic force on the ring to determine the force on the bar magnet. And from Newton's second law, I can update the velocity and position of the falling magnet so that I can build a graph of velocity versus time. In the real-life experiment, I first used the magnetometer in my smartphone to find the end pole of the bar magnet and make it pointing up, and then use the phone to record the magnet entering the top of the tube and leaving the bottom, and I record the time 5 times to get an average total time. I used an aluminum foil instead of a ferrous tube because the ferrous tube may attract the bar magnet and affect the time that I recorded. Then I compared the time for the magnet to fall through the tube with the time for the magnet to fall for the same length in free space. All my measurements are shown on this slide, and the time for it to fall through the free space is much less than the time for it to fall through an aluminum foil. The next few slides help explain my computational model. The code simulates the magnet falling through a conductive tube using the dipole moment that I calculated in Lab 3. In this part of the code shown on the slide, I plug in the physical constants, the real-life measurements, and the numerical parameters of the simulation. This part of the code helps me visualize the bar magnet and set up the functions for the magnetic field and d-flux over dt. And in the next part, I calculate the gravitational force, d-flux over dt, and the current in the ring using the Ohm's law. This slide basically shows how I use Newton's second and third law, and according to the function F equals to B cross IL, I got the magnetic force on the magnet. So this is what it's like when I run the code. While the magnet is falling through the tube, there are currents induced both above and below it. The blue and red rings represent currents flowing in different directions. I will explain more about the directions later. And the figure on the right shows the graph of the velocity versus time. We can tell that the velocity dramatically decreases in a short time and increases to a constant value later when the magnet was in equilibrium. And the time in the tube calculated by the computer is 2.759 seconds. Since the north pole of the magnet is at top, the flux through the rings below the magnet is increasing while the flux through the rings above is decreasing. According to Faraday's law and the right-hand rule, the current below the magnet will flow clockwise and the current above it will flow counterclockwise. Thus, the red color in the previous slide corresponds to the clockwise current, and the blue color corresponds to the counterclockwise current. If I flip the magnet around, the direction of the dipole moment is the opposite, so the direction of the current flowing above and below the magnet would change to an opposite direction too. However, the magnetic force would still be pointing up and shorten the falling time of the magnet. Here are my answers to the next 2 reflection questions. My total time in tube measured in real life is less than the time in the computed model. And I think the computational system would be more accurate if the mu value that I plug in at the very beginning is more accurate. For the next question, I can tell from the velocity versus time plot that the velocity decreased quickly at the beginning and increased to a value that was constant through time. And this told me that the net force was increasing greatly at the very beginning and decreased to a constant value, which was in equilibrium with the gravitational force. In conclusion, the total time in the tube is bigger when computed by the code than measured in real life, because in real life the resistance of the tube is bigger than in the computational model, so the current is smaller in real life. And in this way, the magnetic force on the magnet is smaller, which makes the magnet fall in a shorter time. And that's it. Thank you for listening to my lab report.